Hi everyone, I'm Stephan and I'll be presenting the effectiveness of discretization in forecasting, an empirical study on neural time series models. This is joint work with Tim, Valentin and Jan from AWS AI Labs and David from Naval Labs Europe. So let's dive right in. As most of you might already know, probabilistic time series modeling has seen a variety of advancements in the past few years. Most of these advancements were specifically targeted at either improving model architectures, like the emergence of CNNs, RNNs, and transformers as effective sequence modeling techniques, or coming up with more sophisticated approaches on modeling the probabilistic model outputs. While we acknowledge that most of these approaches have played a key role in improving forecasting performance, we also found that a systematic assessment of the effects of input and output representations, a line of research that has been pursued very extensively for image data, for instance, has not been performed for neural time series models to date. And that is precisely what we set out to achieve with this study. Now, before we dive into our main contributions, let's briefly discuss the general setup we will be using throughout the talk. We're given a set of possibly related univariate time series Z and wish to predict the future on some of these time series in a probabilistic fashion. Each time series Zi is composed of equally spaced values from the real numbers and further comes with a vector of associated covariates xi. You can see a graphical depiction of this in the left column on this slide. In a global model, we then wish to parameterize the conditional distribution of future unobserved values using a neural network. Given such a model and a distributional assumption about the time series values, the model is then trained by minimizing negative log likelihood. During training, a number of windows are sliced from the collection of time series, and values lying in the context range of the time series are fed in as inputs into the model, and the model outputs are then compared to the actual observed values in the prediction range. Our central goal of this work was to develop and survey different kinds of appropriate input representations phi and output representations psi, which you can see highlighted in blue in the information flow graph on the right. Now, to motivate why we felt that this was an interesting issue to dig deeper into, let's first take a look at one of the main challenges forecasters encounter when training global models, which was one of the main drivers behind this work. And that is the scaling problem. On the left, you can see a plot of 3 randomly chosen time series from the M4 hourly dataset. You can already see that their scales vary widely, with the green pattern being clearly visible, while the blue time series appears like a flat line. In the bottom, we can see the CDF across the entire M4 hourly dataset. This plot shows us that most of the time series are on a rather small scale as the CDF increases rapidly at first, but there's a decent number of time series with large values and some additional outliers. In global forecasting, such widely varying scales are not uncommon, and if we want our model to extract patterns like trend and seasonality from these series jointly, we need to make sure that our model can make efficient use of the data at hand by making it easier for the model to model the underlying data distribution. One approach that is often used is to scale each time series by their mean. We can see that this already yields time series where the patterns are more clearly visible. While the step also seems to make the CDF less extreme, some outliers still remain. As a final step in this transformation chain, we perform a CDF-based transformation on the scaled collection of time series. We can see that the patterns yielded by this transform are even clearer, and that the observed empirical CDF turns into the CDF of a uniform distribution over the value interval. We will get to know this transform soon as a probability integral transform in the next slide. I quickly want to emphasize that, while it should not be surprising that feature pre- and post-processing have a large effect on performance in ML models, the scaling problem highlights a unique challenge for global forecasting models, and that it is worthwhile finding effective transformations to mitigate this problem. So, as we can see, the scaling problem is of utmost importance in global forecasting. Let's quickly summarize what we have discussed in the previous example. We got to know 2 effective continuous transformations. The first of them was a simple affine transformation known as scaling. In its general form, values can both be standard and scaled, while the most widely used version, which is classic mean scaling, only performs scaling. However, there are a lot of possible variations of this general form presented above, like the trimmed mean or the median, for instance. The second one was the probability integral transform, which is a popular data pre-processing technique. It maps a random variable z through its CDF into a uniformly distributed random variable, which is easier to deal with. Let's now move to discretized representations, the core element of the study.
we can discretize time series values through a binning function b, which maps real values to binning indices 1 to b, with b being the binning resolution. Each binning index b is linked to a bucket sb. A real input z is then mapped to the binning index b if the value z falls into the bucket defined by b. This raises the question how to choose the edges for each bin. There are two main strategies. The first one is equally spaced binning, which constructs buckets to be equal in width. While this is easy to implement, it has one key drawback. It is only optimal for uniformly distributed data. In the plot below, you can see both an exemplary data density over C and the corresponding equally spaced binning with 10 bins. Clearly, the bin edges are independent of the data distribution. The second, more sophisticated approach is quantile binning, which adapts the bins to fit the data distribution and therefore constructs buckets which are equal in weight or mass. This can be done by evaluating the quantile function of z at equally spaced quantile levels, which then returns the quantile-based bin edges. Comparing the plot on the bottom right to the plot on the bottom left, we can see that the data density is reflected in the bin edges, with high-density regions, like the 3 pronounced peaks, being mapped to fine-grained bins, and low-density regions, like the valleys after the first and the last peak, being assigned to wider bins. Concretely, we propose two main binning strategies, local absolute and global relative binning, and a hybrid binning strategy which allows us to combine multiple binnings. In local absolute binning, each time series is binned individually. For that, we estimate a unique binning per time series and pass each time series through its own binning. This effectively scales all time series to the same interval, since each time series is mapped to values between 1 and b. In global relative binning, on the other hand, each time series is first scaled by its mean and then passed through a single global binning estimated on the entire training set. This also discretizes the series, but still allows us to maintain some relative scale information among time series, as one can clearly see in the giant plot. We can also combine multiple local absolute and global relative binnings, for example using multiple binning resolutions. First, we compute the representation for all binnings we wish to consider. Then, we compute the embedding for each binning, which is a common technique to enable neural networks to make efficient use of discrete inputs, and concatenate the binnings on the embedding size dimension. We chose to evaluate a variety of I/O representations based on the following models. A simple feed-forward neural network, which is just a 2-layer 40-unit MLP without any normalization or regularization tricks, an autoregressive CNN architecture known as the WaveNet model, and an autoregressive RNN architecture specifically designed for forecasting called DeepAR. For the output distributions, we compared 3 different approaches for modeling the probabilistic output. For reevaluated outputs, we considered both the student t-distribution and an approach to model the distribution's quantile function directly using piecewise linear splines. For bint outputs, we considered a standard categorical distribution over the total number of bins. We set up a large study on 9 total datasets to compare different I/O representations on the models described beforehand. Our main results are organized into varying the output representation with a fixed GRB bint input and vice versa. We found that the output representation has a large influence on model performance as measured in the loss delta magnitude. For example, we observed that in the case of the WaveNet model, the lowest loss value was on average 1.7 times lower than the worst observed loss per dataset, with the largest difference being a factor of 3.6. Our results specifically showed that the WaveNet profits a lot from bint representations, as bint representations are the best representation method per dataset in 8 out of the 9 total datasets, and specifically global relative binning showing the best results in 7 out of the 9 total datasets. Interestingly, DeepAR's performance deteriorates with bint representations, with the loss value being on average 2.6 times worse than with default mean scaling. On the other hand, while also non-negligible, we observed that the input representation seems to have a smaller effect on the overall performance. Overall, there's no clear one dominant strategy. However, we found that multi-scale hybrid binning seems to work well in a lot of cases. The local absolute binning strategy consistently performed badly, which hints at the fact that losing the magnitude comparison of different time series amongst each other is a key drawback. Lastly, we found the input binning resolution to have a surprisingly small performance effect, while performance improves steadily when providing more output bins. So in summary, we see that picking an appropriate I/O representation can be as important as selecting a good model. Before closing, we would still like to encourage you to have a look at the paper online and to check out GluonTS, a probabilistic time series modeling library for Python maintained by the forecasting team at AWS. And that's it from our side. Thanks for having had us, and enjoy the rest of the workshop.